Hey everybody, probably the first useful thing to observe about our large number here is that there's 54 digits. And that's not, it's a little tricky to see it actually, but notice that we start with 19 and then it's consecutive after that. It's 19 juxtaposed with 20, 21, and this is a 54 digit number. 54 digit number ends at 45. Now, kind of a standard, semi-confusing combinatorics thing is to take 45 and from it deduct 19. But then you have to add 1 because 19 and 45 are both included. That's slightly confusing, but that's equal to 27, right? So there's 27 pairs, so to speak, and that of 2 each, right? So that's 54. 54 total digits, all right? Now, another thing that I think is a little more useful, it's my opinion at least, is that in if you formulate this problem as n as a congruence, it would be n congruent to r, where r would represent the remainder upon division by 99, mod 99. Okay, so the rest of the way we'll be trying to get an answer in this form so we can just read off r. And of course, I didn't say it, but we're looking for an r between 0 and 98 inclusive. And actually, that's implied by the definition of a remainder, I guess. All right. Now, something that is kind of useful right here, of course, is to write it in its Hindu-Arabic format. And notice that if you take a look here, 44 is equal to 10 times 10. 43 is equal to 10 times 10 times 10 4 times, right? All right, and so you have these successive even powers of 10 pushing these digits to the left until you get to 19 and you've pushed it 26. There are 26 zeros after that. Okay, so again, this took me a little bit of time here. That's slightly confusing because you don't have a power of, this would be times 10 to the 0 if you wanted to see it. But anyway, this is the Hindu-Arabic expansion or the expanded form of the Hindu-Arabic digit. Okay, and so now another useful fact here, though, this is just a massively large number, is to observe that 10 squared, which is our first power right here, is congruent to 1 modulo 99. But one of the joys of congruences is you can treat them very much like equalities most of the time. And so right here, you can also write 10 to the 2n. This would imply that 10 to the 2n, where n is just a natural number, is congruent to 1. Right, folks? You can literally square both sides. If you square this side, you would get 10 to the 4 is congruent to 1 squared, which is 1. If you cube this side, you would get 10 to the 6 is congruent to 1 cubed, and so on. So in general, 10 to the 2n is congruent to 1 modulo 99. Now that's super useful because all of these exponents are in the form 2 to the n. This is 2 times 13. This is 2 times 2, right? Okay. And also, yeah, I left out, you got to leave out stuff somewhere, but what happens here is all of the powers of 10 raised to an even just turn to 1, right? That's why this literally goes away. This is, I'll write it upside down, congruent to 1, right? So notice how all these 10 to the even powers are congruent to 1, and so our equality, and this is pretty cool right here, our equality, oops, that doesn't look right, shifts to a congruence, a triple equal sign, if you will, or triple bars, whatever, you know, a congruence situation. So you have this going on, and now the problem simplifies immensely. Notice how 45 just kind of rode along, right? Okay, now what do we have here? Well, we have the sum of the first 45 integers minus the sum of the first 18 integers. And there's a very well-known formula for that, and you guys have seen it. I hope I have room here. Do I have room to write this down? That this is the result summation I equals 1 to n is equal to we put an I right there in the sum n. That's n times n plus 1 over 2. These are sometimes called the triangular numbers because if you draw them up just right, they look like triangles, rows of a triangle. So y'all, what I did is I applied this. I hope that's legible, folks. I is the index of the summation. I is also the sum n. And when you sum up the first n integers, this is a result. Well, no result. You can prove it fairly easily. But that's exactly what happened right here. You see, this would be the sum of the first 45 integers. But that's not what we have. We have the sum of 19 through 45. So you have to subtract off from it the sum of the first 18 integers. Okay, notice 18 would appear just before 19. And so when you do the arithmetic, you get 864. Okay, get 864, and then right down here you see, so this entire summation gets replaced with 864 because it's physically equal to 864. All right, and then I think you have, what do we got? 864, I believe, let's see, 864 is equal to 8 times 99, I believe. 8 times 99 plus 72, which is where our magic number 72 comes from. Pretty sure the arithmetic's right here, folks, because see, that would be 800. Yeah. 8 times 99 plus 72 is equal to 864, but that means this part right here is congruent to 0, right? 99 is the same thing as 0 mod 99, right? And so that's where we get our answer, folks. 72 is the remainder. Okay, so let's go back. So the remainder would be 72. Okay. Good night.